Good morning, everybody. On behalf of Imperial College, IX, and most importantly, the IX MIT Center for AI in Science, I would like to welcome everybody. My name is Sofia Alazraki. I'm part of the center, and I'm a professor in chemistry. It's very exciting to have this program today. It's all really state-of-the-art AI for science work that has been accepted in the most prestigious conferences, so it's amazing to have you here. I think it's also in the spirit of what the center is trying to do. This is the third year for this kind of conferences, and I think what we will see is how the level is getting higher and higher and accelerating. One of the important things of what the center was trying to do is to bring people together from different areas to catalyze and fertilize these interactions. And one of the ways to do that is co-location. So when you do go for what has been promised by Eileen, coffee and food, you will see this area that is full of offices from people from different departments, a lot of breakout areas where it's really important to discuss and get ideas from different people, which is exactly what we hope this conference will do. We all come from different backgrounds, but we have the same passion on how to actually get into science discovery by using AI tools. So equally, hopefully, some of the questions we're trying to answer will feed back into these AI tools development themselves. Another important aspect of the center is bringing together early career researchers. After all, you are the present and the future. And in a very new area like that, this is where all breakthroughs come, bringing all of you together. Also interacting with more senior people that many of them are around as well. So this is really important, and it's great to see this reflected in the conference as well. So without further ado, I want to give the floor to you and hear what you have to say. And most importantly, use the day to talk with each other and make this day go further than it is now. And that's really what we've been trying to do and continue to do. So we are going to start with Paula Cordero Encinar from our StatML program here at Imperial. And we're very excited to hear what you have to say. Thank you.
Okay, hello everyone, and thank you for coming. So today I'm going to present this work on sampling by averaging done in collaboration with Andrew Duncan, Sebastian Reich, and Denis Agildis, where we propose a new sampling framework that combines ideas from diffusion and stochastic, multiscale stochastic system to tackle an important problem, which is obtaining samples from a probability distribution. So why is this an important problem? Well, in many areas of science, chemistry, physics, machine learning, and statistics, we sometimes need to estimate the expectation of some function over a probability distribution. So usually this is done using a Monte Carlo estimate, but to do that, we need samples from our probability distribution. And this might not be easy to obtain in every case. So the problem is that if, for example, pi is a Gaussian, then it's so easy to get samples from it. Like there's been a lot of study on how to get samples from these distributions. But if pi becomes more multimodal, then this does not become, this is not straightforward anymore. So the distributions that we'll be tackling correspond to high-dimensional, multimodal, heavy tail, and in all these cases, they are normalized. So we don't have access to the full probability distribution, but just to an unnormalized version. That is, we're missing the normalizing constant. So there's been mainly study in classical MCMC techniques, but these techniques, they usually struggle with these multimodal high-dimensional cases. So these MCMC samplers, they deteriorate in high dimension, so the scaling with dimension is terrible. They also if we have like many modes in our probability distribution, they might get stuck into one of them and then may not be able to sample the whole space. Also, if you're familiar with MCMC, they will require a long burn-in periods. So this is not ideal in terms of computational efficiency too. So many of you might have heard about diffusion models. So the idea under diffusion models is to interpolate our probability distribution with a simpler one, and then trying to sample along this path. So that is, instead of sampling from the initial probability distribution that we need to, we tackle the problem progressively. So we sample from a smooth probability distribution and along a certain path. So there's different ways in which we can construct this path. So for example, in this picture, I've illustrated the geometric and the diffusion path. So the geometric here on the left, and the diffusion one on the right. So in this case, we're interpolating between a Gaussian-based distribution at time 0 and our target, which is the combination of a normal distribution and a smoothed uniform distribution with a very small weight. So we see here that the geometric path has some multimodality along the path. So this is not ideal because we know how to sample very well from convex log concave distributions, but when we have multimodality, our samples might struggle. So therefore, we see, for example, that diffusion path might have better properties than the geometric path over here. So in the previous picture I've shown, the diffusion path, it's basically given by interpolation of the base distribution, which usually in the previous picture it's a Gaussian, and our target distribution using a certain schedule. So when at lambda t equals 0, lambda t will be, so lambda 0 will be equal to 0. So therefore, we only have this term over here, where lambda, at t equal to 1, lambda t is equal to 1. So we just have our target, that is what we want to get. So the probability distribution associated with this interpolation is basically given by a convolution. So the convolution is usually, to compute the convolution, we need to solve an integral. And this is not easy for. So therefore, even though this diffusion path have very nice properties, mathematically it's not tractable. So we need to find some workarounds to use it. So the idea to be able to leverage this path is to use this Langevin dynamics. So this equation basically, so mu t is the path of distributions that we want to sample from. And we are drifting our distribution so that it follows that path. So in the homogeneous case, so when we don't have any time dependency, then the Langevin dynamics is warranted to convert under certain assumptions to the stationary distribution. So in general, so we hope and we show in the paper that this distribution converges, follows the path that it needs to follow. However, a key obstacle is that we need to estimate this score term over here. And this score term can be expressed as an expectation of a known expression. However, the expectation is with respect to this distribution, which is related to this one, but not exactly. It's, however, it is still not tractable. So we know the expression of this, but we don't know exactly how to compute it. So in the generative model case, that is when we have access to initial samples from our probability distribution, people, what they do is to use score matching techniques. So if we have samples, for example, like images from our probability distribution, then we can noise them and be able to estimate this expression over here. However, in the sampling case, we have access to the normalized probability distribution. And this rho t over here is given basically, like to get it, we need to solve an integral, which might not be easy because usually our probability distribution would be very complex and this is not tractable. So just to recap, the idea is to use this, as in diffusion models, this forward noising process and then the reverse noising process. So basically we sample along this smooth version, smooth path that interpolates between two distributions. If the scores were known, that is, if this lambda is this grad log mu t was known, then would have a robust sampler. It would scale well with dimension, and we would be able to get samples efficiently to estimate different expectations with it. However, as I said, in the sampling case, we don't have data, so estimating this score is not tractable. So what has been done in the literature? Because of course, we were not the first one to think about this idea. So many of these works, what they did is to compute this expectation over here so at each step of the diffusion, they would run an inner loop to try to get samples from the distribution. So at each time t, they pose the main sampler, that is this sampling over here. And they run an inner loop to obtain samples from here so that they can estimate the expectation. However, this is not efficient because it means that like at each step, we need to stop, sample, like do an inner loop and then keep going. And then, so if we have like many time steps, this becomes very computationally expensive. It also, it's very sensitive to hyperparameter tuning, these methods in general. So we thought, how can we leverage the diffusion path without needing to needed to run an inner loop to get samples from there? So our key observation is to approximate this expectation on the fly. That is, using an alternative process which has a faster time scale that is able to directly get us samples to estimate that expectation. So we don't need to do like two levels, like two loops. So to do that, we introduce multiscale stochastic system. So the gist and their multiscale stochastic dynamics is that we have a system of two coupled components. So we have our slow process that I will name xt, are our fast process, yt. So the fast process over here, it has a time scale 1/epsilon. So where epsilon tends to 0, the scale of this process, it's much faster than this one. So for example, imagine that you have like a hummingbird and a tortoise. So while the tortoise wouldn't have basically like moved forward, the hummingbird would have go to a tree, get a fruit, and come back and give it to the tortoise, and the tortoise wouldn't have noticed that the hummingbird has left. So the idea is that this slow process doesn't notice that y has explored its entire space. So y is able to explore the entire space, arrive to its stationary distribution, and x wouldn't have noticed. This means that we can use yt to explore the conditional distribution that we needed over here, and x wouldn't have noticed. So we can plug in that estimate to estimate the expectation. So just to emphasize again, y explores the entire space, reaches equilibrium, and xt has stayed the same. So xt doesn't see that yt has moved. It only experiences the average behavior of yt. So as I said, we can replace this complex yt by with its average, that is the value that it has arrived. So if we have like original drift given by this expression, we can average over the stationary measure of Yt. And we can plug in that estimate to obtain the average drift, that is this value over here. So here we have this expression that would be what it's inside the integral. And then when we average this expression with the stationary measure of y, we get the average drift, which is the original one that we want to get to be able to sample from our path of probability distributions. So another, like a recap of this, we, like this main idea, we introduce this fast variable, Yt, which rapidly explores its space and reaches stationarity. The slow variable will evolve according to this drift. So grad log mu t, that is the score that we wanted, can be expressed as this bxt yt, where yt has explored its space. So it's approximating the expectation that we needed. So the things that this algorithm solves is that we don't require this inner-outer loop, and it's also training-free. So we don't need to use any computationally heavy neural networks to approximate this drift term. So for general noise schedules, this grad log mu t that I said before, it's the expectation of some unknown known expression. In particular, this known expression can be computed. So this is very similar to what you might have heard called Tweedy's formula. But in the general case, so Tweedy's formula is just restricted to having a Gaussian-based distribution and a certain Ornstein-Uhlenbeck noising process. But in general, we can express this using like this generalized formula. And so, as I said, for general noise schedule, we have this, but we also have this equivalent expression, because we know that since the convolution is symmetric when we differentiate, we can either differentiate we can differentiate either of the components and get to equivalent expressions, sorry. So we see here that when lambda t approximates to 1, this expression will blow up. So when lambda t is equal to 1, we instead use this expression, which is not treatable with lambda t is equal to 0, because then this will blow up. So we can play with these two expressions to sample from it. And these expectations are approximated by a fast variable. So while here we have this expectation over here, based on the ideas from multiscale dynamics that I introduced before, we can just plug in our Yt estimate over here and get the system that we wanted. So here we have our fast process that evolves with a scale 1/epsilon. And then we have our true slow process, that is the one that we want to sample from, given by these two processes based on these two generalized Tweedy's formulas. So by averaging over the limit when epsilon tends to 0, we recover the initial diffusion over here. That was our goal. So by averaging, we recover our original true path. So we are able to sample from it. And instead, we implement an accelerated version to be able to be like be faster and also don't get stuck in some of the modes. So we tested our method in a wide range of distributions. So we tested in different like multimodal Gaussian mixtures, heavy tail distributions, which is more complicated because in that case, instead of interpolating with a Gaussian, so instead of having nu, which is the base distribution, to be Gaussian, we have nu to be a heavy tail distribution. We also show the performance on high synthetic examples and also on a statistical physics system. So we show that our method has a competitive performance against alternative methods that are also training free. And also the computational efficiency of it's much better since we don't need to do this inner loop to target to obtain the score. Another key observation is that the algorithms that we propose, they are robust to hyperparameters, and they show a stability across these hyperparameters. So for example, one key parameter is the scale separation. So it's important to select it carefully, because if we choose a very small epsilon, then it may be numerically unstable. However, we cannot choose a very big epsilon, because then we wouldn't have a big, like the scale separation that we want to be able to experience the ideas for multiscale stochastic dynamics. However, we show that even though there's an optimal value over here, when we move the value of epsilon, the performance will not explode. So there's like a range where we would have decent performance. And on the other side, we have the number of steps. So the performance, it's also robust under the number of steps. So we see that like if we do more finer steps, so if we do finer time discretization, then we'll have a better final error, so the lower the best. However, there's we see that the performance doesn't blow up in this case under the number of steps. So just a recap. So we propose this multiscale stochastic sampler that combines ideas from diffusion and multiscale stochastic dynamics. We introduce two different algorithms. I've also only introduced one of them in this case, but if you're interested, you can check for more details. And these algorithms are training free. They don't require inner-outer MCMC loops, and they're also efficient for heavy tail distributions. So this provides a unified framework that combines ideas from sampling, diffusion models, and stochastic SDEs. So that's it. Thank you so much.
Thank you so much for a wonderful talk and opening the day. Questions? We have time for questions, so please. I guess while people are getting... Oh, there you are.
Hi, thanks. Thanks for the interesting talk. I had a question, maybe just to understand better, I would imagine the same scenarios where MCMC, et cetera, doesn't work very well. Mm-hmm. This may not also work very well in terms of sort of this computation of the average drift. So it's like, how quickly are you, can you give an example of where this will converge significantly better than MCMC, or vice versa, if that also exists? Because I would think that the same scenarios of like long tailness, et cetera, where MCMC doesn't work, is also where sort of doing this average drift idea will also not work. Thanks.
So one thing that we observe is that so we use this version, but also an underdamped version when we include some momentum. So the the normal version without that momentum was struggling, especially where we have different weights for the different modes. So when the modes are not equally weighted, it was struggling because it was not assigning the correct mass. However, using the underdamped version, it was helping to assign better, closer to the correct weights. But I guess that was one of the main things where it struggles. So if it's very multimodal but equally weight, the weights have the modes have equal weights, then performance is good. Unequal weights, it's where it mainly struggles to assign the correct ones.
Okay, thank you. So maybe I'll ask a question. So, you mentioned this issue of the multiple time scales, but also the high dimensionality, right? And many times in a physical problem, we understand that. At other times, we don't. We don't know that before. So I wanted to ask you, on top of the sampling savings you're making with this, is there a way that you find signatures of something physically going on in your system that you wouldn't find in the MCMC? Is something you've thought about, or?
So in terms of, can you?
You're getting those paths, right?
Yeah.
So is it only that you're getting faster sampling, or also you get access to some physical process that is better than standard methods?
Yeah. So I guess this diffusion path, it's interesting, as you said, because we have this whole interpolation of distributions. So it has some interesting properties, because then, for example, we can also leverage that to estimate the normalizing constant. So that gives us some interesting properties that we can leverage in different cases. So I guess it doesn't only come with the idea of faster, the benefit of faster sampling, but also I think you made a really good point of having some intermediate or extra information from these intermediate dynamics.
Thank you. Any other question? Okay, well, we have the coffee break too. Oh, please.
Thank you very much for the nice talk. I know that in traditional diffusion models, some people have tried to use sort of equivariant layers so that if you know the distribution you're trying to approximate satisfies some symmetry, you can sort of force a diffusion model to be preserving that symmetry. Is it easier or harder, do you think, in your method to have symmetry preserving?
Yeah, I think that's something that we thought at some point. So in this case, it's not that easy because we're not in our case we're not imposing anything on this drift term, but you can my idea was you can always add some extra constraints on your problem to be able to preserve that symmetry. And especially in the non-training free case, so when they train a neural network to approximate a drift in the sampling case, I've seen some works where they try to preserve this symmetry, because you might have some information about your problem that you want to incorporate. And yeah, I think that's a very good point, and I think that might be able to also be included in this.
Thank you.
Thank you. Okay, well, let's thank Paula again for talk. And I hope all these discussions continue with coffee and lunch and so on. So our next speaker is also from Imperial, but different Department of Computing, while Tolga will be setting up. We'll take a moment. Oh, I'm looking forward for the new hope for molecular modeling, Tolga.
Well, you would like to do. No?
Thank you so much.
Interesting. Is this the only way? Yeah, it's this one. Oh. I guess. I think. Do I have a clicker somehow? Also. Do I have a clicker as well?
I think it's
Ah, okay, perfect. This one. Good. Ah, yeah, okay, perfect. Yes. Okay. Cool, cool. Hi, everyone. Should I start, Sophia?
Yes, please.
Okay, yeah. Yeah, good, excellent. I am very happy to be with all of you here and sharing these NeurIPS papers that normally I don't get a chance to, to read and stuff. So thanks for explaining all of this in the following hours. I'm going to share our NeurIPS paper, but I have to give you an introduction of why we do all of these things we do today. And I think it's going to connect to a broader topic. So the beginning of it is not going to be immediately about the paper, but later on it's going to come. So it's very hard to start, I think, an AI talk today without really showing these impressive things that our community has achieved in the past. So you enter a prompt, just like a little text over there, and a video model, for example, could generate all these beautiful stuff, right? And we are all quite impressed by this. And we are curious, can we take that to other fields, right? I mean, when it's basically the data that you share across WhatsApp, so text, images, videos, audio, then the performance is really good. But if you are dealing with any other data type, we are not there yet, right? So, if you were to ask a, ChatGPT kind of thing to generate you some kind of a protein that is going to be docking to a specific virus specification, like whatever that you scanned, it's probably not going to be able to do that, right? And the situation is the same across different domains. So if you go to CAD design, if you go to, I don't know, self-driving cars, well, maybe it's a bit better because it's image-based, but there are other self-driving cars that are LiDAR-based and the performance can be a bit worse. Or neuroimaging and medical imaging, so on, we are still struggling. And there are reasons for that, okay? Now, it's not so I'm not going to solve every single problem in these domains, but there is one specific reason that if you work in the domain of 3D vision long enough, you understand immediately that it is a fundamental problem. So it's the representation. And what I mean by that is exactly this. If you take your phone, and if I tell you that I took a picture today with my phone, you exactly know what I'm talking about. All of you agree that I recorded a matrix of pixels where each color encodes an RGB kind of a color value, okay? But if I tell you that I have a 3D model in my hand of a building, you really don't know what I'm talking about, actually. So it could be a point cloud, it could be a voxel grid, it could be an octree, all these mathematical surfaces, it could be a level set, SDF, you name it. It could be a mesh in computer graphics, right? And of course, this gave researchers the nice freedom to kind of go ahead and say, oh, I'm going to invent a new neural network for every kind of representation that I see around, and this way I can salami publish a NeurIPS paper every year. Right? It's amazing. So, and people actually did that. If I were to list all of these, it would probably go down the building with that. Yeah. So they really did that. And I think it's kind of ignoring the underlying problem that we don't know how to process this information in 3D space, agnostic to the representation. Okay, so we are trying to kind of address this in a big research program called Topological Deep Learning. And we believe that it has use cases in certain fields. Okay, this includes, well, the domains of molecules and proteins, which are complex enough that you don't want to hand model them all the time. Or like CAD models, like people come up with all these heuristics to process the boundary representations, and there are many other forms. And we like to consider all the domains agnostic to what it is. Okay? And we want to first come up with data structures that can represent these domains, and then come up with a stack of deep learning algorithms that can work on these and kind of transfer the success of deep learning in image domains or text domain to these domains. And for that, we are going to use what is called the relational data. Okay. So usually, at this point of time, if I present you some kind of a data like this, okay, that's presented in the form of relations, and you can think that the relations are sets. So here I'm giving you the set AB. That means A and B are connected. The set ABC indicates that all the elements are here are interconnected, so kind of a higher order relation. It's not a pairwise relation anymore. It means that the daughter, the mother, and the father make up a family. Okay? That's what it means. So the family is a unit on its own, so this is a set on its own. So it could be BDEF, so that means it's a fourth order set. Okay, so currently, here is what you do. You get such a data, you say, oh, the thing that I know that works quite well are the graphs. So I'm going to partition these relations into a set of pairwise relations. So I'm going to take ABC, for example. I'm going to make AB, AC, and BC out of it. I'm going to take BDEF. I'm going to decompose it into how many? Many, larger than 4, pairwise subsets. And I'm going to think that a graph can approximate this quite well. Right? But the problem is the connection between BDEF as a unit is completely lost if I do that. For example, if you take a 3D mesh of a surface, right, there's an underlying continuum that the mesh represents. And if you just say that this is composed only of edges, then it's a loss of information immediately. And this is something you can picture very easily. Right? And this happens agnostic to the domain and agnostic to the dimension. Okay. So to kind of cure this a bit, we introduced this notion of complexes. So this comes from algebraic topology. I'm not going to do a lot of mathematics, but a bit. So you can see that there's a graph on the left-hand side. So there are the vertices 1, 2, 3, 4. And then there are the edges that connect them. For the purposes here, I'm going to talk only of sets, whether it's a singleton or not. So whether it has one element or it contains a lot of elements. A lot of elements just means that it's a n-way relationship. Just a single element means it's a vertex. Right? So edges are as equally important as the vertices here. Or you can have a triangle that connects 1, 2, 3, and this would just be another set in addition to this. So it's kind of a subset of the power set of the given vertex set. Okay? So you could also start defining now orientations of it, just like you do as in the directed graph case. And you can say that I'm going to go from 2 to 1 or 1 to 2, right? And you could do this when you are presented with a face as well. You could say that I'm going to rotate from 1 to 3 from this, So if you have a mesh, for example, that you want to compute the surface normal, you would assign an orientation. You would use your right-hand rule, whatever you prefer, right? And then you would say that this mesh is pointing outside the center, so towards the camera or so, right? Here it's the same logic. So you can assign this orientation, then your sets become vectors, basically, right? It's an ordered set now. Good. So now, just like you would, for example, you would go from vertex 1 to vertex 4, right? In a graph, what you would do is you traverse the edges. You go, first one edge and then the second edge. So these are essentially your paths to the desired vertex, right? You do that because you cannot really walk over the faces themselves. But now we have the faces available, so these triangles are filled in. That means there's a kind of a set in my data structure. So it's not a graph, right? That corresponds exactly to this face explicitly. So I could actually make use of this and kind of start walking over these faces as well. Okay. Well, fine. So, it's very convenient, by the way, to write this traversal as a linear combination, a weighted linear combination of these elements. And on the case, as you see on the right, these elements would be, 1, 3, 2, for example. So the cardinality is greater than 2. OK, so what I'm really talking about is that you can think of graphs as vertices that are assigned to edges, kind of. Right? And then hypergraphs, for example, they would just have these hyperedges, right? They would completely lose this, this notion that edge is just connecting two things. So they would just abstract away a lot of things at the same time. They would also represent higher order relationships, but they would lose the hierarchy immediately. So here, these cell complexes, that are, again, we are not doing this. These exist. So the vertices are assigned to edges, but then these are also linked by higher level cells. Okay. Good. So in the classical sense, you would take a point cloud like this. You would say that this is a zero-dimensional cell complex. And you would glue them with edges. Okay. So you just stick those edges on top of the vertices, and you would get a graph. It would be a one-dimensional cell complex. You could then also take your faces and then stick them on top of that data structure you have. And then you would get a two-dimensional cell complex. And you see immediately this is already not a mesh, because you have this triangle plus you have this square, right? So these are different order cells. It's a more general mesh. Okay, so to process graphs, right? At some point in your life, somebody comes to you if you work on graphs and tells you that Laplacian, there's Laplacian, and it's very important. So you really need to first compute the Laplacian and then do everything else. It takes a while to digest this. Right, you make the connections to heat equation and all that, and all these interpretations of Laplacian. But anyway, you realize that a lot of convolutions and message passing operations and so on and so forth can be realized through Laplacians. So what people do, well, you see a decomposition of Laplacian here. It's a decomposition into boundary matrices or incidence matrices that is basically encoding for each vertex the relationship to the edge. Okay, if a vertex is connected to the edge or attached to glued to the edge, it's a 1 or -1 depending on the direction, and that's a boundary matrix. It encodes the boundaries of edges. But now if you have some kind of a higher order thing or a cell complex, right? Here is a simplicial complex because all of them are just triangles. You would have another boundary matrix, B2, which links edges to triangles. Okay? And you could compute from this another Laplacian. But now, since your order is growing, so 0, 1, 2, right, you could compute the same Laplacian in two ways. You could say that, I'm going to do B transpose, so BK transpose BK, okay, or BK plus 1, BK plus 1 transpose. These are, if you think about it, they both generate. So in this case, if you take B1 transpose B, right, it's edges by edges, a matrix of edges by edges, and the other thing is also edges by edges. Okay, so in one of them you come from down, the other one you come from up. So if you combine them, this is known to be a Kate-Hodge Laplacian. So this is kind of the analog of the graph Laplacian that you have for these domains. So now you can kind of make use of this object to define your message passing algorithms and so on. Right? And so in a recent paper, well, not so recent anymore, we came up with this generalized object called a combinatorial complex, which links all of these together. So the points and graphs and, well, hypergraphs and so on. And it's kind of a unifying representation. So if you can represent your data in this form, which almost all data that we know are kind of representable, then we give you a neural network that can work on this. So the idea is generalization here. Okay? And you see that the more kind of explicit capacity you build on your data structure, the more things you can represent natively. Okay? Like the raw thing, the raw object that you process in your neural network starts to carry more information. So it's not just you kind of make the abstraction like a graph and ignore all information first and then hope that the neural network is going to recover them if you train them on a giant amount of data. But this is rather saying that, well, I'm going to put as much inductive biases as possible to the object, to the data that I work with, and I'm not going to lose information at will like this. Right? So you can start to, represent the world of chemistry in more hierarchically and kind of more proper manner. Okay? Well, depending on the time. 10 more minutes. Okay. But anyway, I think we defined this a little. But okay, so this data structure. So in the graph, when you think of a graph, you would really just think of a vertex and an edge. Okay, so vertices and edges, nothing else. Not all the cycles and faces and stuff. You need to run an algorithm on your graph to get them. They are not there. Okay, but this thing actually has them by construction. So you have a set S. Okay, this is all. By the way, there is no edges or anything in the world. There is only this data comes in the form of a set. Okay, like all the other things we do, a graph is an abstraction, is a convenient abstraction that you make. So your social network is not a graph. It's only a graph because you ignored the families. You didn't store the families or communities in there. Right? So any data that comes like this, graph is an abstraction. Okay? Graph is a choice. It's not in the data. So here we just say that, well, I'm going to take S. This is my set. And then I'm going to consider the subsets of the power set, which is X. And X, of course, it's a subset of basically all possible relations that you can build out of this set. Okay? And then I'm going to take a rank function that kind of encodes the hierarchy. So the rank, so if X and Y are two relations in this X, okay, if X is included in Y, then its rank should be lower than the rank of Y. So this is, if you have that, then you have basically, you have a mechanism to order the dimensions. Okay. So the trick is in defining neighborhoods. So I give you the set, and normally, for example, if you work on graphs or point clouds, if I ask you who are your neighbors, you would say, oh, I'm going to do an epsilon ball query, right? Or take the KNN and just assign myself to the nearest vertices that are around me. So here the situation is a little interesting because around you there are edges and faces and vertices that are treated equally within the same framework. So you would say, well, which neighborhood, right? The face neighborhood, the edge neighborhood, or the vertex neighborhood, are you asking, right? So you start to define this notion of higher order neighborhoods, which themselves are combinatorial complexes also, right? So you take a point cloud, you query the epsilon neighborhood, and you would get another point cloud, right? So it's the same. You take a neighborhood, right, and then if you extract it out of your combinatorial complex, it by itself represents a combinatorial complex. Okay. So the idea is that now we have the vertex set, and we know how to define a complex on it. Okay. This is the art, okay? This is the design of these neural networks. And then once the complex is defined, you choose how to define your neighborhoods, right? What to link, kind of. And then we give you the deep learning stack on top of this. Right? So many of the research that we do is on the last part so that we could actually do those things. So the simple one would be, well, take the most stupid graph convolutional network that you would have on the left-hand side. So you take the data, multiply it on the left by the adjacency, on the right by the learnable weight matrix, right? And then you pass it through a nonlinearity. This is known as a graph convolution, kind of. Well, you could actually do the same, but now this adjacency, which is defined through the Laplacian, you would define it through the kth Laplacian, okay? And that gives you the ability to define your convolution along different ranks. Yeah? So it's not just one. So you can go crazy with it and build these interesting convolution operations. But of course, graph people tried this, and they immediately backed off and said, well, we are not going to do convolutions like this because all these convolutions that come from the eigenvectors of the Laplacian and so on and so forth, they have some kind of they have problems. So let's do instead message passing, okay? And they said, well, this is going to be a bit better, if I design my message passing right. Here we can also do the message passing, and in fact, it's a hierarchical message passing. So the messages are first passed within the neighborhoods, okay, within different neighborhoods, and then another message is passed from these neighborhoods to the central node, or the central entity. I want to call entity because it doesn't matter if it's an edge or a vertex anymore. Okay. And then the message for that entity is this double aggregation. So you can really think of this as a hierarchical kind of message passing that goes, from neighborhoods to the considered dimension. Okay. So once these are there, now you can stack layers on top of each other to kind of come up with these deep learning algorithms. Okay. And then train all these learnable components of the message passing over some data. So what we did in this NeurIPS is to find a way to speak about these structures in a very general way. Okay? So there's a bit of category theory, so don't get scared with the language. But what happens is, there's an object called a presheaf, okay? So this is like on a directed graph, for example, you would say that every node, on every node, my data represents kind of a vector space, okay? So that means, you really have all these nodes have their own spaces where the data is defined. So this means, think of an image where at one point you store an RGB color value. On another point, it's possible to store the depth in the same thing. Okay? I know that it's a bit weird, but it is possible. So these are different vector spaces at each node. And then you define a way to kind of pass messages from these vector spaces to another vector space. Okay? That, and as you see that this remarkably generalizes, it gives you a super big freedom. Of course, the cost is that because it's not specialized enough, maybe the specialized architecture, the better engineered architecture, can do certain things better. But it's not going to take you all the way to a general deep learning framework. Well, so we also defined this co-presheaf message passing neural network. Okay, so we defined message passing on these objects. And we also did this not just for graphs, so I'm writing everything here for a graph, but also for the combinatorial complex. I don't want to complicate it, further than this, because it can get really ugly very soon. But essentially, you are trying to learn some maps. You can think of these as linear maps also, from some vector spaces to other vector spaces. In our case, it could also be neural networks. Okay, and we also did define attention mechanism on it. So we also have the attention mechanisms over combinatorial complexes in general. And the name of the game is to show that, is to show that this, first of all, can represent any data, and all possible message passings that you know in the literature could be written in this same framework, okay? So you take any neural network, there's a correspondence specification of the map we learn and the data structure we work on that is going to recover the message passing you tell me. So you can think of this as geometric deep learning taken to the extreme. right? Okay, so this is a bit better. Right, and there are so many papers that do, for example, sheaf diffusion stuff and message passing over Laplacians and so on. So everything falls into this framework now. And we also use these objects, by the way, to construct diffusion models. And you have listened to a very nice talk, and it is possible to, for example, say, well, I'm going to generate a graph, okay? And then I'm going to diffuse a graph. But this is so weird to come from a complete noise to the target graph. Like, this is not like if you do that in the image space, right? The pixel grid is intact. You are not touching it. You are changing the signals that are defined on the image. So this diffusion works really well. But if you diffuse a graph where you want to infer the connections, then you want to kind of diffuse the structure of it, and that's a bit of a different thing. So that means, for example, if you want to maintain the topological integrity of the diffusion process, then it would be nice to kind of say, well, I don't want to just diffuse through every trajectory. I want to diffuse through trajectories to go to higher order skeletons, which actually makes sense. Right? So kind of let me generate the coarse components first of the graph, and then diffuse these pairwise edges. It's possible, and you see that across several metrics you could actually get improvements. So you can see, for example, that on the top row what you get with this kind of diffusion, and on the bottom row the typical diffusion processes that people do. Okay, so you see that there is in these diffusion. I mean, maybe the final object that you get is okay, but like this. It doesn't look very nice to diffuse this way. It looks almost completely random in terms of connections. It's a bit insane. Okay, anyway, we provide a lot of source code. And we are writing a book on this as well, on this repository called TopoX. Okay, not everything is up to date, but it's very, very usable, very testable repository if you want to work on these things. Yeah, and we work on this within my group, which has been at Imperial for 3 years. So I have to shout out to all these people and a lot of collaborators that I worked with in this field. And so I'm just one of these guys, basically. Yeah, thanks. If you have questions.
Thank you very much, Tolga, and also for the introduction. And I couldn't agree more that solving a computer science problem and a science problem is not the same.
Yep.
Yeah, and I think that's quite important to keep in mind always. Questions, and then I can ask.
There is one.
Where?
Or two. Yeah.
Oh.
Hi, can you talk more about your rank function and how it is agnostic to edges, vertices, and
everything is
bases?
agnostic to edges, so we don't differentiate them. These are sets, right? So you see that everything is basically a set here. So having a set with cardinality 1 is nothing particular here. Well, so if you really go deep into the mathematics, there would be people who can find problems with talking about singletons this way. But let's take that mathematical details aside. So the rank function is basically anything that where you realize, you say that the vertices are 0 rank, edges are 1 rank, and then, and you just keep track of the dimension, right? And, well, you could, of course, say that your one-dimensional objects are edges, but you don't need to make that naming. I mean, you really don't need to come up with this. These are essentially all sets, and they kind of have different cardinality. And assigning cardinality is one thing. You could think of other rank functions as well that are not dependent only on the dimension of the object. That's up to the creativity, I guess. Yeah.
Hi. So in regular message passing networks, neural networks on standard graphs, you get oversquashing issues from oversquashing and underreaching. Do those appear as well in higher order in these hypergraphs.
Can you ask again? Maybe I didn't get it.
So in regular graphs, you get issues with message passing where.
Oh, like you mean over smoothing, over squashing?
Exactly.
Like
yeah. Do those appear as well in these settings?
I mean, so this is a very good question. I always believed that these would have less, because, like, for example, you can pass messages. Like, let's say you are at two distant nodes, okay, from source to target. There's a big path, and you want to pass a message. And if you pass the message directly, there will be some over smoothing. So what people do is they define a virtual cell, virtual higher order cell of, let's say, rank 2, okay, which is going to encapsulate all of this. So you instead of linking these together, you link everything to the virtual cell. And then you kind of message pass over this virtual cell in a bit of a different way. So I always thought that this would, overcome some of the over smoothing issues around. But then there's a recent paper, also by a talented guy, who says like topological deep networks also suffer from these over smoothing. So I am not making that claim anymore. I think there are issues, and these should be studied. And in the spectrum of the graph Laplacian is very well studied, but the Hodge Laplacian spectrum is less apparent, like the mathematical properties and stuff. Or like there are issues. So if you want to get good spectral properties, then you have to choose how to define your Laplacian to conduct all this analysis. Not all Laplacians are great for spectral properties in higher order networks, if that makes sense. So yes, somehow there are issues, and these theoretical issues we have to work on as well. That's true, I think.
Okay. Hi, Tolga.
Yeah, hi.
Thank you for a great talk. Yeah, so that's a brilliant idea to design the complex convolution. Yeah, but my question is here: when you're talking about the embedding of the existent graph or complex, it's quite clear. But when we're talking about the reconstruction or the generate such a complex, so sometimes even for the regular graph, it's really hard to reconstruct the connectivity, right? Yes. So the complex situation goes worse. Yeah, you have to design which people will usually use attention or something to predict the probability from two pair. But when we go through the complex, how you deal with that?
Okay, so there are two problems here. First of all, I mean, so what I have done so far is to generate a graph in the end. Well, in the end, okay. And that we use the higher order information as kind of a guide, right, to maintain the integrity of the generation process. The reason why I cannot really speak of generating higher order cells, unless it's a molecule or something, what does it mean to generate this? Like, what does it really mean for a higher order cell? I mean, it's a very philosophical question, because you could essentially pick any order you like, right? There is always so let's say you generate a graph. I mean, you can detect communities, right? And they are there now because you detected them. So higher order cells are there by construction. I can speak of all the higher order cells. So which of these ones should I generate? And what does it mean to generate this? Should I generate something that I could already compute from the graph? Or should I come up with something completely interesting and novel? So this is why I couldn't touch that exactly. But I think if we find something around this, then something is doable. It's an open question, I think. I'm very happy to work on it.
Thanks for you. But the basic example for here is just a geometry generation. We want a mesh, but we have random sample from the mesh.
if you
reconstruct the space.
Sure, that would be an easy way to think about it. And there, higher order relations have an exact physical correspondence. This is not true in arbitrary domains.
Okay, thank you very much.
You had a question, and then we have coffee break.
Thank you. I just want to ask, so with graphs, there's n choose 2 possible edges. With triples, it gets bigger and bigger. So how does this scale in the, because there's too many possible of these subsets?
I think this is also a beautiful question, which was also puzzling me for a good amount of time. First of all, it scales horribly, right? It's exponential in the number of dimensions. I mean, but surprisingly, nature is beautiful in that sense. It's not generating higher order cells without necessity. So this bias for simplicity is also causing the amount of, so in a molecule, I mean, she would know much better, how many higher order connections do you really have? It's always a couple, like a handful, right? Even for large graphs, even for large molecules, right? So although the amount of edges are increasing and the theoretical complexity is scaling horribly, it just doesn't happen in nature that everything is connected to everything. In fact, a much, much sparser set of higher order connections are present, right? So that is the luck that we have. Yeah. So it doesn't need to scale. Yeah.
Thank you. Yeah, I guess in the similar vein of these questions, I guess there's, since your message passing operations are neighborhood based, there's some equivalence here to, you could define a neighborhood based simple graph which accounts for the neighborhood structure at the kth dimension, right? And then you could probably do simple message, like simple graph message passing on that equivalent neighborhood structure.
Yeah.
So is there a sense of equivalence there? Or if not, then why is this sort of containing that set of models?
Yes, there is a data structure level equivalence. So you can, in fact, kind of take that higher order cell and then turn these higher order connections to vertices themselves, kind of like doing the dual operation, and then connect these vertices to all the other things that this face was connected and stuff. So you could actually take the data structure and map it to an equivalent graph, which is called a Hasse graph, by the way. And then that is okay. The problem is now you define the algorithm. So you take that algorithm that is operating on this. You don't know anymore how this is not equivalent. How the algorithm runs, like your algorithm that you define, this message passing, to be able to define the same message passing here, you need to do a very counterintuitive operation. You see,
maybe this is a good time to stop, yeah?
Sure.
We can do this on the board.
I mean, so you have the data structure, okay, so x1, and then you have the graph G, okay? So this is a combinatorial complex, let me call it CC, and then you kind of run an algorithm on it, okay? Let's say A1, and this is going to give you some kind of a result X. And now you want to run an algorithm on this that gives you the exact result X, yes, okay? Transferring this is easy. This, we don't know.
But there is a statistical equivalence in terms of the learnability. Right?
There is an axiomatic equivalence between the data structures. There is no axiomatic equivalence between the algorithms. I mean, there is, but finding that algorithm is exceptionally hard sometimes. So this gives you a better design space, essentially.
Great. Thank you, Tolga and Paula. Let's thank both our speakers and all of you for this is what we want. And please, let's continue. I have tons of questions too. I mean, you're working with our student, Michael, right?
Yes.
Yeah. So we've thought about some of these things.
Yes, of course.
I think this is quite interesting. Anyway, please, let's continue the discussion over coffee. And let's try and be balanced in it. I'm not sure if we have to split in the middle, but...
Fine. Everybody to my right, the coffee is there, everybody to my left.
It's fine.
We start faster that way, trust me.
Trust you.
If everyone could take their seats, we're about to start the next session. Thank you very much. Okay, great. It's my pleasure to chair this next session, where we're going to be having 5 10-minute flash talks. I'm going to invite our first speaker to the stage. So that's Kevin Han Huang, who's going to be talking about neural network solvers for the Many-Electron Schrödinger equation. So you've got 10 minutes. I'll give you a pointer at 1 minute.
Okay,
Yeah, thank you.
1, go. Right, this is going to be a short talk, so I'll try to give an overview rather than going into a lot of technical details, and feel free to talk to me about any questions afterwards. My name is Kevin. I recently finished my PhD at UCL GASP unit in machine learning, and I'm currently a postdoc with the Pro AI Hub working with work statistics and Princeton operational research. My main research interests are more in sort of the theory of machine learning with applications in scaling laws and AI for physics. And this is sort of one of the more applied stuff that I'm working on. And this is an ICML paper that was accepted, and it's joint work with my amazing collaborators, Jenny, Ryan from Princeton, Peter, my PhD advisor, as well as a physicist, Elif from UIUC. Right. So I want to start with quoting a slide from one of the favorite people I know in the field, Gabor, who gave this IPAN talk about sort of AI for large-scale atomic simulations. So people talk about AI for physics a lot and AI for physics simulations a lot, but actually the problems can be categorized in very different scales. And depending on the scale at which you are looking at your materials, actually the kind of physical constraints, the kind of neural network models that people look at are very different. Our work is basically looking at this very fine scale, right? So when you have very few atoms, but then you are sort of really zooming in into details to look at the electron space, and you are trying to ask how the electrons behave. So this is a space where you have relatively little sort of physical measurements to get from, but then it's also a scale at which people know that theoretical models are really good descriptions of what's going on. So our main task is basically going to be solving the Schrödinger equation, which is known as the good theoretical model for describing things at that scale. And this is going to be an n-electron sort of Schrödinger equation. So you assume that your atoms are basically fixed, but your electrons are sort of behaving like wave functions, and they are sort of traversing around the atoms. And you want to try to use maybe some sort of neural networks or computational methods to get an accurate description of how the electrons behave, which can inform you on various properties of the materials. And if you've done some quantum physics in undergrad, so you know most of the heavy lifting is sort of in this V, this potential function that's determined by your material, right? So if you have like one-dimensional sort of toy potential, then undergrad math or physics courses will take you through working out what this wave function looks like analytically. But for most real-life materials, that's definitely not possible, and especially not possible when your number of electrons are quite large. So this is where sort of neural network comes in, or as well as non-neural network methods. People try very hard to use a lot of computational models to sort of fit in this equation to try to get the best approximation possible for the wave function. I'm going to emphasize that this is an ab initio kind of method, and what that means is that unlike most machine learning training paradigms where you try to fit your neural network onto training data, there is no training data here. Right? Your objective is really just trying to use neural network as a sort of search engine to find the best fit to the Schrödinger equation as much as possible. And a lot of the heavy lifting is sort of in trying to model these functions when n number of electrons is large, and also getting wave functions that capture the correlations between your different electrons as a function of your materials. And that's So needless to say, neural network has sort of like revolutionized this field sort of over the past 3 to 4 years. The search space for this kind of problem is still really large because you're not just searching in the R3N space, you're searching in a function space, like of R3N to C kind of functions. And one of the favorite sort of things that people like to do in the AI for science setup would be to use some kind of symmetry structures. So here we focus on a particular symmetry that's in crystals. And what I meant by that is, for example, if you look at a graphene, and I'm using this toy object to illustrate the symmetries in a graphene, right? So you do know that when you are in this particular physical system, there are certain rotations and reflections and translation symmetries that your electron wave function will have to obey. So that gives you some constraints on how your target neural network should look like. And I think I'm going to skip this slide. It's like a little bit more technical. But the point I want to emphasize here also is that crystal is actually known as a somewhat harder problem than a lot of the examples that people would see, because we really care about restricted rotations, restricted symmetries here. So imagine if you just naively put in a neural network that's invariant to all rotations, then you're really throwing out information from a lot of the angles that you're not supposed to be invariant to. So here, when I'm with graphene, I know that around this atom, I exactly should have this sort of six-fold symmetries, right? So that's sort of what makes the problem hard. And a lot of neural networks, self-hard neural networks, don't still implement this because these kind of symmetries are quite hard to incorporate. But I'm taking a picture of like a state-of-art network for this kind of like crystal problems. And you can see that if you visualize the wave function that it has learned, it has approximately learned that kind of symmetries, this sort of like hexagonal symmetry that you're expecting from graphene. So you do know that at least the well-behaved neural networks are trying to obtain this symmetry. And the question is, okay, can I try to build these kind of symmetries into the neural network solvers? Interestingly, the answer becomes quite nuanced. So there used to be a time where we also believe that you should add symmetry to neural networks and everything should work. But over the last 2 years, actually there's been some really interesting work that's pointing out that symmetries may not necessarily improve neural network training. And the prime example is the very recent version of AlphaFold, where they're highlighting that they are explicitly removing a lot of symmetry structures from their previous versions. And there are also papers in AI for Science that are conjecturing that if you constrain your neural network too early, maybe that's preventing your neural network to explore as much of a space as possible, and it's leading to performances that are suboptimal compared to ones that are not constrained. We don't have a full answer to this problem in our setup, but we do have, we don't have a full answer to a problem in a general setup, but within our problem, we managed to basically identify where symmetry hurts and where symmetry could help. And it turns out to be something that's very specific to how this kind of algorithms are run, and it's related to the earlier talks, actually. So remember I was saying that our task was to fit the Schrödinger equation. And to be more exact, we actually only care about finding the ground state wave function for that Schrödinger equation. In our mathematical formulation, that's just finding the minimum energy or minimum eigen solution corresponding to, the eigen solution corresponding to a minimum eigenvalue of that problem, right? So at a very high level, what people do is to try to reformulate the whole problem of solving Schrödinger equation into one that is looking at energy minimization. And in particular, right, remember originally I am trying to search in an infinite dimensional function space, but then with neural network I've reduced it to a finite dimensional one. With this sort of energy parameterization, there's a very nice property of electron wave function in physics, which is that you can directly relate the wave function of electron to the probability distribution of where the electron appears. That allows me to write my objective as an expectation over this electron distribution, which I'm effectively parameterizing with neural network and trying to learn. This allows me to write all my optimization methods in terms of the expectation. The difficult thing is that distribution is exactly what we want to learn, so that's something that we don't actually know in closed form. That distribution is very high dimensional and also not really normalizable. Computing normalizing constants is very expensive, as already hinted at Paula's talk. So in practice, I think the clicker is not working somehow. All right, thanks. So in practice, and I'm going to talk about this quickly, how people train neural networks is that they run this kind of optimization algorithm where they know that there's this expectation that I really can compute explicitly. So I run a bunch of Markov chain Monte Carlo methods to try to get examples from it. But I'm restricted to running really short MCMC chains because I actually have to do this gradient descent sort of across many, many, many iterations. I can't afford to run my MCMC chains long enough that when I actually get the unbiased expectation. And then once I've learned a wave function at inference phase, I then run very long chains to accurately compute this expectation. And that allows me to compute various downstream properties with respect to these electrons. And what that meant for us is that because this whole procedure is so computationally expensive and there are all these paths that introduce various biases, when you start to incorporate symmetries into your neural networks, you have to be very careful about the computational cost it incurs to your neural network. So our very first message is that there's a bunch of traditional symmetrization methods, which I won't have time to go into in detail, but that these methods which would have different computational costs associated with them. And it turns out that if you want to incorporate some of these conventional symmetrization methods, you are forced to reduce the batch size that you're using in your training updates. And that causes you to have gradient destabilization. A very, very high-level intuition why this is interesting is in traditional neural network training, you have a fixed-size training data, and then you do symmetrization over them. In this kind of setup, your training data at every optimization step is actually examples from your MCMC. So you could always draw more IID examples if you want to. Right, and what you end up is basically there is a trade-off between drawing more examples or symmetrizing the existing examples that you have. And we find that actually doing symmetrization during optimization almost always hurts the performance, both in terms of gradient stability and the overall performance. What we end up proposing, and sorry, I think the click, okay, thank you. So what we end up proposing is for people to train your neural network just as it is without any symmetry constraints. And then at inference time, you use this sort of group averaging method to then enforce the symmetry constraint on your trained network. And I don't have much time left, so I just wanted to say that very surprisingly, I think this post hoc method actually beats, so the black curve is like state of the art. Existing network without symmetry and all the other curves are various symmetrization methods. This post hoc averaging method actually beats the performances of all those other networks, and we were able to run this on really large scale experiments and get up to a 10 times computational speed up in terms of raw GPU hours for getting the best wave function in some of these materials. So that's everything. Thank you.
Thank you very much, Kevin. We have time for one quick question, if anyone has a question. Yes.
Thank you. So in the end, you are trying to kind of come up with a model for physics, right?
Yeah.
And I believe there are a lot of physicists who are working on this problem. And I was wondering if they are happy when you remove their most essential component, that is the symmetry, from this equation?
That's a great question. So it turns out most methods in this field don't even incorporate this symmetry that we were considering into that. And that's for the reason I was saying that for this kind of crystal symmetries, it's way harder to incorporate compared to periodic symmetries and all this other stuff that people do incorporate. And in this space, even with those symmetries, there's sort of interpolation between classical methods and neural network methods, where, as you were hinting, people sort of drop more and more physical constraints as they move to neural network methods. And those neural network methods tend to produce better benchmarks that are useful for specific physics applications. But then when you want to move to other physics applications that require certain physical properties, then those things fail. And right now, a lot of the research is basically trying to bring these two together and trying to argue. So it's basically not really possible to incorporate all the physical constraints that we want, but for certain applications, can we afford to forego certain of the constraints? Yeah, thank you.
Okay, thank you very much, Kevin. Let's have another round of applause. So our next speaker is Cristiana Diaconu. Hello. and she is going to be talking about gridded transformer neural processes for spatial temporal data.
Do I turn this? Okay, awesome. Hi all, and thank you very much for inviting me here. Today I'll talk about some work that I did with my amazing collaborators on gridded transformer neural processes for spatio-temporal data. So gridded TMPs, gridded TMPs, as we like to call them, are a flexible probabilistic framework for dealing with large-scale unstructured data. But before delving into the method, let me first explain what I mean in this context by large-scale and unstructured. And to do this, I will use kind of like this guiding, motivating example of weather forecasting, but this doesn't mean that the method is solely applicable to that. So lately, you might have seen that there are a lot of like AI models in there modeling weather coming from both the big companies as well as research labs that are able to surpass the accuracy of traditional numerical prediction methods, all at a fraction, at a cost. And I think that the main reason why we managed to get there with weather forecasting is because the data was very much ready from a machine learning perspective. So the weather forecasting agencies managed to collect these very high quality data sets containing the outputs of numerical weather simulators that basically describe the best state of the atmosphere at each point in time over a very long history of time. And this representation is what we would call in this talk structured, gridded, or on the grid, in the sense that each variable is represented as like a very high resolution grid of pixels where each pixel corresponds to a certain surface area, say 25 kilometers squared. So it's very much kind of like, a nice representation, meaning that the data was very much machine learning friendly and ready to use. And this is indeed the data that is being used in the AI models, the majority of AI models out there. Now, what we are arguing is that there's another source of very important data, which is the unstructured or off-the-grid data, coming, for example, from in-situ observations, so things like weather stations or ships or balloons. And the reality is that this data is much trickier to work with because it exists at arbitrary spatial locations. And so this kind of like brings me to like a summary of the challenges from the field. So first of all, it's just the sheer volume of data. Each variable is quite a high resolution, as I said, image, and it's not just one variable that we're modeling, it's about 140, and you also have to take into account the time dimension. So this is tricky. But I mean, we're not the first ones to deal with this, and this is a problem that has, been out there for a while, and people from, for example, the computer vision community have found ways to deal with this by, for example, employing efficient attention mechanisms, such as the vision transformer or SWIN transformer. And again, these are the techniques that are being used in the current models out there. But unfortunately, they're not applicable out of the box to this unstructured data that we're trying to use. And this is what we're trying to address with gridded TMPs, to basically enable the use of efficient attention mechanisms, all while keeping a probabilistic treatment, which is crucial for spatio-temporal tasks. So let me give you a very brief primer on neural processes. They are a technique that maps data sets of arbitrary size and structure to probabilistic predictions at arbitrary output locations. So let's say that we have some unknown function that we're trying to model, but we're only observing the black dots, which are called the context data set in this case. And neural processes basically make predictions at arbitrary output locations, so for example, that xt over there, by outputting the parameters of a distribution that we're pre-specifying. For example, the mean and standard deviation of a Gaussian. And they kind of like mix these three concepts, but I won't go into too much detail about this. Out of the best performing variants of neural processes are, perhaps unsurprisingly, the transformer neural processes using a transformer backbone. But in our case, because we're dealing with context sets of hundreds of thousands, if not millions of data points, well, they're inapplicable because of their quadratic attention cost. So we need to do better. And this is what we're doing with gridded TMPs, which are a flexible and scalable way of modeling this data. They're composed of three main components: an encoder, processor, and decoder. The encoder basically just takes our context observations, which, as you can see, are unstructured. They can lie anywhere in our space, and then just embeds them point-wise into higher dimensional representation. So nothing fancy happening here. Now, the processor is kind of like the main bit of the method, where the idea is that, okay, we want to use efficient attention mechanisms. They can only operate on grids. So this means that we somehow need to project our data, our unstructured data, onto, let's say, a pseudo grid and do the processing there. So what we're doing is that we're taking our context tokens from the encoder and then learning a projection into a grid of pseudo tokens through a cross-attention mechanism. Then we're doing the processing on this pseudo token grid. And then at prediction time, we're querying at arbitrary target locations, again through a cross-attention operation to output the target tokens that are then fed into the decoder to output the parameters of our distributions at each target locations. In terms of the experiments that we considered, we kind of like tried to find settings where other methods would not be applicable out of the box. The first experiment was trying to predict the temperature at 2 meters at weather stations around the world. And as context information would give them some information from a subset of stations, as well as information about the skin temperature, which is a related variable and is coming out of these numerical weather prediction models. And the task is to predict the remaining station locations. And then the second one, in spatio-temporal modeling, quite often we want to model multimodal data. So in this case, we chose 6 wind-related modalities at 4 consecutive points in time. And quite crucially, so at each point in time, we were only modeling the observations over the US, but for the 6 modalities, they are not observed at the same spatial location, meaning that you cannot plainly treat them as different channels. In terms of results, we kind of like show that gridded TMPs outperform some of the state-of-the-art neural process method that existed up to date, which is a method that uses a convolutional neural network backbone. In terms of the way you're doing that projection onto the grid, we kind of like looked into 2 different methods of doing that. So first of all is the kind of like pseudo-token approach that I already mentioned, which is based on a cross-attention mechanism. A simpler baseline is something called kernel interpolation, where you basically have like your context points over here. You're first constructing a continuous representation by plugging some radial basis functions on top of them, and then discretizing that continuous representation. So this is kind of like a simpler method, and we're showing that the cross-attention one, perhaps unsurprisingly, surpasses that. Then we're also comparing the use of SWIN transformer versus plain vision transformer, and in this case, SWIN gave better results at a lower computational cost. And then finally, because we're operating in the spatio-temporal domain, we know that there are certain inductive biases, symmetries, as the previous talk was mentioning, that are potentially useful. So the idea, for example, of translation equivariance, that if you're moving your predictions in space and time, you would, your observations in space and time, you would expect your predictions to move accordingly. And so we have, we're comparing in here the variant without inductive bias with the 2 variants with inductive bias built in. And that further boosts performance, but perhaps more importantly, it leads to much better generalization properties. So in the wind experiment, which is the right-hand column, in there we were only training over the US region, and then at test time testing over Europe too. The model without inductive bias fails catastrophically because it's never seen that, whereas the one with inductive bias maintains good performance. So that's about it. Once again, I want to thank my collaborators for this work. And yeah, if you have any questions, I'm more than happy to answer them.
Thank you very much, Cristiana. Perfectly on time. Hold on. So any questions for Cristiana?
Yeah, because you mentioned you are doing this unstructured data because they can be any arbitrary locations. I'm wondering if that can be used for using some continuous representation techniques for processing this, like maybe Gaussian splitting or implicit neural representations.
Yeah, I mean, I guess even like with the kernel interpolation one, right? Like in there, basically we're like sticking radial basis functions on top of each context point, and that leads to this continuous representation. And you can do more and more advanced techniques. And I think there's actually like quite a lot to be studied in here. Whether like that's a better alternative to the cross attention, which will obviously come with its own cost. And yeah, so that's kind of like a very valid point, and we haven't tried that. In our case, yeah, like this cross attention worked very well, but I think there might be, and also depending on the domain, a better representation in terms of how you construct this.
Okay, one very quick question.
So to add to this, so my question is, why don't you use a point cloud transformer, actually? Because it's a point cloud in the end. So when you map it to a fixed grid, what you are doing is, if all the points are clustered around some of the grid points, then they are mapped to the similar tokens, and then your discriminated power is going to go down drastically, no?
Well, right, but at the same time, like I think if they're kind of like clustered, then it's kind of like maybe there's like a more compressed representation of that points that you can obtain. So because you have like a lot of information there locally, and because in general the spatio-temporal data will have a lot of like locality inductive bias, then you might not waste so much by compressing all of those into that one pseudo token. But again, like that's, it can be empirical and it be quite domain specific.
Okay, thank you very much.
Thank you.
Our next speaker is Hugh Dance. Where's Hugh? Hello. Who's going to be talking about efficiently vectorizing MCMC on modern accelerators. Thank you.
Can everyone hear me? Yeah. Not sure it's on, but I'll be loud enough. Just give it 1 second. Okay. Yep. Hello? Oh, yeah, there we go. Okay, thanks so much for inviting me here today. My name's Hugh. I am a PhD student at the Gatsby unit, which is part of UCL, under Professor Peter Orban, so that's the same research group that Kevin recently departed from. And my research is kind of in 2 different lines. I'm yet to connect those lines, but in causal inference and scalable probabilistic inference. And today what I'd like to talk about is work that was recently accepted to ICML. And basically the idea behind this work is to try to find a new way of implementing what are called Markov chain Monte Carlo algorithms for sampling from distributions in a way that can much better leverage the power of modern hardware like GPUs and TPUs. Okay, so I'll go straight in. So the setup, one way to motivate what we're doing is to think about this canonical problem of estimating expectations from a distribution. So suppose you're interested in an expectation of some function of x, and x has some distribution pi. And in many situations, whether you could be training a large energy-based model, or you may have done Bayesian inference, and you're interested in computing a posterior expectation downstream. In those types of settings, we often only know the distribution of this x, or rather the density of this thing, up to a normalizing constant. And so what that means is we can't directly compute this expectation by just trivially using numerical routines to sample from this distribution. We need a particular bespoke way of sampling from this distribution. And so a tried and tested formalism that's been around for, well over 50 years now is what's called Markov chain Monte Carlo. And what Markov chain Monte Carlo does for a particular distribution of interest pi is sort of 3 steps. The first thing is you construct a Markov chain, and that Markov chain should have a stationary distribution pi. So in other words, that Markov chain, if I draw samples from it, those samples should eventually converge in distribution to the distribution of interest. And so once I have that chain, in practice I would implement this Markov chain in computer software. And for the purposes of this talk, what's called the transition kernel, the function that we use to iteratively sample from the Markov chain, that'll be implemented by this function I've highlighted in red called sample here. And so for a particular MCMC algorithm, we would sample iteratively as shown in step 2. And then once we've drawn our samples,
we can eventually estimate this expectation by just simply taking the average. So just to point out, this is not a new technique. Markov chain Monte Carlo algorithms have been around for well over 50 years. There are a host of algorithms that apply to large classes of these distributions. What we're interested in is trying to implement these things as efficiently as possible. Okay, it's been also known for a long time that these MCMC approaches are embarrassingly parallel. If you have m different machines, so there I'm showing 2 GPUs on the right-hand side, you can run m or 2 chains in parallel on these machines. And so then rather than drawing n samples per second, I now obviously have m times n samples per second. And the obvious benefit to doing this is that when you think about that problem of estimating the expectation, if I run my chains for long enough so that we converge closely to that distribution of interest, the variance of our estimator should decrease linearly with the number of chains we're running. So we can actually get like an m-fold speed up if we have access to m machines. And that's really drove a lot of the sort of research. There was a good chunk of research in MCMC about 20 years ago that was really focused on efficient parallelization on many CPUs. But in the land of GPUs, things have changed slightly. And the idea is now to say, can we try to get the most out of a single machine rather than having to distribute the code onto independent machines or processors? And the way in which people try to leverage the power of a single machine more effectively is this notion of what's called vectorization. So vectorization is really the process of transforming a program that naturally acts on a single data input into another program that acts on multiple instances simultaneously. So here I've shown this function that we're going to be using to draw samples from, iteratively for our Markov chain. You would wrap this thing in a function, and the name of that function will depend on the framework you're using. JAX, which is quite a popular framework in MCMC, the name of this tool is called VMAP. When you pass that function into VMAP, you get a new function out, and that function will act on batches of inputs automatically. Basically, rather than writing your code in a way where you've had to manually make sure things are batchable, it does all the batching for you. And there are big benefits to doing this. So the idea is if you have access to multiple machines, rather than doing one chain per machine, within each machine, I can now run a batch of these inputs at the same time, or batch of these chains. And so here I've shown a very simple example where I've run a very classical Markov chain Monte Carlo algorithm that is a really simple algorithm that just has a few straight line. It's basically a straight line program. And here what I'm showing is as I'm increasing the number of chains that I deploy on each of these GPUs, so in this case a single A100, the number of samples per minute that I'm drawing effectively is going up broadly linearly, up to the GPU capacity, which tends to hit in at around a warp size, which is 64 threads. And so basically the story here is that, well, this looks great. We can now not only distribute code on multiple machines, but we can also run many, many chains on a single machine and massively improve the efficiency of our inference. But there is a problem. And the problem is something that isn't unique to MCMC, but does pop up in MCMC more often than for other types of algorithm. And that is when your program contains control flow that is input dependent. So things like while loops, that's the main focus of this work, where the length of that while loop is random. Or maybe a for loop that also has a random amount of time. And the problem is that these automatic tools that I showed, they have to transform your program in a way that enforces that the GPU executes the same instruction at the same point in time for multiple data inputs. And so for things like matrix vector calculus, that's straightforward. We've got advanced kernels under the hood and arithmetic logic units that are very good at doing matrix vector calculus in a way that seems almost simultaneous for multiple batch members. But for things like loops, it's not clear how to batch a loop. And so the paradigm that's kind of emerged in many compilers and machine learning frameworks is this idea of what's called the sort of run and mask paradigm. And what that basically means is, what essentially that results in here is if you have a loop that's being run in our program for each batch member, to run that, to turn that into one piece of code so that every batch member runs the same piece of code, we have to turn this into one while loop for all the batch members, and it has to have one termination condition, an aggregated termination condition, instead of an individual termination check for each batch member. And so when you think about what that means, if this loop takes a random amount of time to run, then each time this loop is called in the middle of your sampling process, instead of just running for the number of iterations that's needed for each batch member, all of the batch members will have to wait and run iteratively until the slowest batch member has finished terminating. So to demonstrate how damaging this can be, I'm just going to show a very simple example with a very popular Markov chain Monte Carlo algorithm in machine learning called Hamiltonian. Well, it's called the no U-turn sampler variant of Hamiltonian Monte Carlo. I'm not going to go into the particulars of this algorithm. I've just shown a graphic at the top, which is an intuition about what this algorithm does under the hood in the while loop that we're concerned about. Basically, what the algorithm does is it tries to explore the distribution more efficiently in fewer number of samples. And to do that, it needs to build a certain trajectory that is given by a Hamiltonian. And the length of this trajectory is random. Each time it doubles, and it does a certain check internally to decide if it should continue building this trajectory. Once it's finished building the trajectory, it'll then take a sample along that trajectory. The point is, it's a random process and therefore takes a random amount of time. So I implemented this algorithm on a very simple mixture of Gaussians problem to just start sample from a mixture of Gaussians. And on the left-hand side, what you can see is the distribution of the number of steps needed to terminate this loop check. And so you can see there that actually with very high probability, we're taking what looks to be a very small number of steps. It's actually about 7, where that large mode is on the left. But every now and then, one of the chains needs to take about 1,000 steps. So if you were running these things independently, each chain would take its very small amount of steps as you're running, and then eventually, every now and then, it would need 1,000 steps, which would be a very slow iteration. But unfortunately, when all these chains are synchronized in their execution on the GPU, we now need to take, what ends up happening is the probability that at least one chain out of 500 takes the very large number of steps is extremely high. And so actually, your expected time taken is going to be basically 1,000 steps every time, instead of paying the 1,000 steps every 100 times. So what we end up seeing here is a slowdown versus what would be optimal of near 100-fold in this case. Not quite 100-fold, probably more like 50-fold in this example. Okay, so we have limited time in this talk. I'll just give a quick overview of how we solve this problem. The basic idea, the spirit of the work, is to try to, we don't want to give up all these automatic vectorization tools. They're very convenient, and MCMC is often a smaller part of a bigger training pipeline. The idea is, can we redesign MCMC algorithms in a way so that when we actually use these tools, we don't incur these large synchronization costs? And so the very high level of what we're doing is sort of illustrated on the right. The TLDR is we want to avoid using these iterative loops where possible, but that involves writing the code in a different way. So rather than writing everything from the ground up again, we have a simple procedure that basically takes your program, breaks it into coarse blocks of code, and then you just have to remember which blocks could be called after the other. And those blocks should be blocks that do not involve input-dependent iterative control flow like while loops and for loops. They can involve things like if-else, straight-line code, but just not input-dependent random time called pieces of code. And so what we're going to do once we've got this factorization of the code is we're now going to find a way of running these blocks that structures the synchronization in the GPU around which state you're on, or in other words, which block you're on, instead of which sampling iteration you're on. All right, just to say quickly, this is something we've sort of automatized for toy languages of programs. Okay, and so what do we do? So that's breaking the program down. Once you've broken the program down in that way, we want to be able to call this thing in a way that kind of mimics asynchronous execution. We would like to mimic the idea that they were running independently on different machines. And so the way we do this is so before there was a function sample that said, you give, wherever we are, we call this function once and we get one new sample. We're now going to define another function called step. And what that function is going to do is just execute a code block wherever the current chain is in the sequence of code blocks. And then it's going to do one transition based on which block should be called next. Now that function can be vectorized in the way that with these automatic tools that are convenient. And now what we can do is when you vectorize this thing and you now run a batch of chains on the GPU, what's going to happen is the GPU is going to run all the code blocks at the same time. And every time it makes a single call, it's going to run all the blocks that make up the program, which wherever the chains are, they will run their respective block and move on to the next block. And so now, so I'm showing here, slightly confusingly, I'm showing 3 states on this graph. The one at the top shows 5 states. They're different algorithms. In this 3-state example, where we've broken the program down this way, when we do this procedure, essentially the chains sort of start off together on S1, then chain 2 in red gets stuck on S2. That's the loop state. So for a number of steps, it's iterating and it's iterating. The other chain, meanwhile, can move on. Whereas if we didn't do our procedure, they would all have to be stuck and no other samples could take place. All right, so just quickly, we do some theoretical analysis in the paper. The only things I just want to say on this page are, first of all, that the sort of bound in efficiency gains is really large. For distributions where essentially the typical time taken to run your loop is quite small, but every now and then there's a very large cost in running the loop, you can see an efficiency bound of well over 100. The procedure I described on the previous pages doesn't always hit this bound, but we do then make some optimizations under the hood, and for certain algorithms like slice sampling variants and delayed rejection algorithms, we do actually hit this efficiency. We have guarantees of hitting this efficiency bound for expensive log likelihoods, which are precisely the log likelihoods that we're concerned about when it comes to computation time. And just to come back to this last example again, so on this example that I alluded to before, where we implement this...
30 seconds left.
Okay, this is our slide, yeah.
Okay, good.
Just lastly, to come back to this problem, so we came back to this no U-turn sampler problem. In blue, you can see the sort of standard best practice implemented in blackjacks. In red, you see our FSM variant, which basically just takes a mild transformation of this algorithm, and we're able to obtain nearly an order of magnitude speed up depending on the number of chains you're running. All right, so I'll just stop there and just say thank you to my wonderful co-authors at UCL and at Princeton, and you can find our paper online. Great.
Thank you very much, Hugh. I'll just give you one quick question, which is, does this work for every type of sampler or just nuts or just basic MCMC?
Technically, you can run it on any sampler you want. If you run it on programs that have no while loops, you won't see any benefits. You can be worse off. So if there are multiple while loops and they don't take a random amount of time, they actually take a fixed amount of time, then you will be worse off. We made some optimizations to try to limit that problem, but we're really worried about the stochastic loop scenario, basically. Yeah.
Great. Yeah. Sorry, we don't have more time for questions, but let's say thank you again. Our next speaker is Yedi Zhang. And they're going to be talking about training dynamics of in-context learning in linear attention.
All right. Hi, everyone. My name's Yedi. I'm a PhD student at the Gatsby unit at UCL. I'm presenting a work on training dynamics of in-context learning in linear attention. It appeared at ICML this year as a spotlight. This is a joint work with my fantastic co-authors, Aditya Singh, Peter Latham, and Andrew Sachs. All right. So a one-sentence summary of our work is that we characterize analytically the training dynamics of multi-hat linear self-attention trained for an in-context linear regression task. So first, why do we care about training dynamics of attention models? It's probably an increasingly important and relevant problem because in the large language model era, we typically do not train our models to convergence anymore. Then we really care about the dynamics, the process of training, not just the converged model, because we rarely get to the converged model. And secondly, it has been found that in-context learning abilities of attention models were just abilities of attention models in general evolve with training time in very interesting and non-trivial ways. So in this very influential blog by Anthropic in 2022, they found that in-context learning of attention models usually emerge abruptly at some time point during training. And more recently, people have found that in-context learning may have algorithmic phases, and there weren't a theoretical explanation for why these things happen. And we're going to see both of these two features in our theoretical setup, abrupt learning and algorithmic phases. All right, so this is why we care about training dynamics of attention models. Then why do we care about training dynamics of linear attention models? So linear attention is the regular attention, but without the softmax normalization applied to the attention matrix. It's analytically more tractable, and it's being found to share many optimization properties with the regular attention. And there's literally a paper called Linear Attention, it's brackets, maybe you'll need to understand transformer optimization. And I also just want to highlight that linear attention, despite its name, is a nonlinear model. Because if you just look at the expression, it's nonlinear in the input x, and it's nonlinear in the weights w. So we're not trying to use a linear model to approximate the behavior of a nonlinear model. We're trying to use a nonlinear model to capture the behavior of another nonlinear model. So maybe it's more believable when people say that it does share many optimization properties. All right, so this is the model, and the task we train this model on is called in-context linear regression. It's a canonical instantiation of in-context learning, and I have here a screenshot of me prompting ChatGPT to do the in-context linear regression task. So I give it a string of numbers, 112, 325, -176, and 48 question mark. I ask it to fill in this question mark. You probably have noticed that I generate these numbers according to a linear map. So I add the first two numbers to get the third number. So the question mark should be 4 + 8 = 12. And ChatGPT correctly answers 12. So this is one input-out pair. And you can do this again with a different linear map. So in the second prompt, I generated the number as, I subtract the second number from the first number to get the third number. So the question mark should be 3 - 1 = 2. And again, it correctly answers 2. So this is the in-context linear regression task. The first 3 rows are called the context of the input, and the last row is called the query. And if I write things with mathematical symbols instead of numbers like an adult, the input is a matrix, capital X. The first n rows are called the context, and it has n pairs of small x and small y's. I generated small y's according to a linear map of small x. And the last row is the query token XQ, and there's a 0 here. I should fill in this 0 number, and the target output is the same linear map W in context applied to that query token XQ. So it's called the in-context linear regression task because what the model needs to do is to do linear regression on the blue numbers in context to recover that linear map W and apply it to the query token XQ. An important thing here is that for each individual prompt, there is a new linear map W. So in the first one, I have 1, 1 because I'm adding 2 numbers. And the second one, I have 1 - 1 because I'm subtracting 2 numbers. So there is a new W each time, and you need to inference that for each individual sequence. If it's fixed, it's just linear regression. It's not fixed, so it's in-context linear regression. And for my actual derivations and experiments, I sample my W from a standard Gaussian, and I sample my small x tokens from normal distribution with 0 mean and capital covariance, covariance capital lambda, right. So this is a task. So we train the linear attention model on this task. I'm going to start from the simple case of linear attention with rank 1 key inquiry. Usually we have multi-head attention with low rank key inquiry, and the rank is a hyperparameter. We're going to start from a simple case and proceed to the more general low rank case. So we train this model on the task with square loss, gradient descent from small initialization, and these are the loss curves. So the different curves are just different random seeds, and what consistently happens is that the loss goes through a plateau and suddenly drops, another plateau suddenly drops and continues, and we find that this is actually saddle to saddle training dynamics. Each time the loss plateaus, it's because the weights are approaching a saddle point on a loss landscape. And we actually calculated the amount of each of these drops and find that they're actually approximately an eigenvalue of the small x covariance matrix capital lambda. So the first drop is approximately the largest eigenvalue. The second drop is approximately the second largest eigenvalues. There are 4 drops in total here because my small x here is 4-dimensional, so there are 4 eigenvalues to be learned. And simultaneously, what's going on inside the weights of this attention model is that they're actually learning the eigenvectors of that covariance matrix. So I plot the key weights in each attention hat during the first, the second, third, and fourth plateau, and you can see that if I see the weights in the first plateau, is that there's the key weight in one of attention hat is growing from small and learns the top eigenvector of the covariance matrix. And the second plateau, he learns the second eigenvector, and it goes on. And it's kind of I have a GIF of this dynamics in the paper. It's kind of interesting to watch because it's basically watching linear attention do eigen decomposition for you. And we can actually reduce the dynamics of each of these transitions to a one-dimensional ordinary differential equation about just one value weight parameter given by this equation. We plot the solution of this equation in dash curves and the simulations in solid curves, and they do agree very well. So now, because we have this understanding of they're doing eigenvalue decomposition under the hood, we actually know what the linear attention model is doing in different stages of learning. So say if you just early stop training right after the first abrupt loss drop, what you get is a model that cannot quite do in-context linear regression. What it does is in-context principal component regression with just one principal component. If you stop training, say after 2 drops, it does principal components with regression with 2 principal components, and then 3, and then 4. And when it has learned all the principal components, it recovers the full in-context least square linear regression solution. All right, so this is the dynamics with rank 1 key inquiry, and promise that we're going to the more general rank R case. And the behaviors are quite similar, except that now learning occurs in chunks of size R. So in the far left panel, I have rank 1 key inquiry, and the loss curve climbs all the stairs. If I have rank 2 key inquiry, it climbs 2 stairs at a time. And what's going on is because it's learning 2 eigenvectors at a time. And then you do principal component regression with 0, 2, 4, 6, 8 principal components. And in the rank 4 and rank 8 case, it also learns 4 things and 8 things at once. So this is linear attention, and we also did simulation with softmax attention, and the previous paper isn't lying. It is doing something similar as linear attention. It also has these stages, and it learns these eigenvectors sequentially. All right, so that's pretty much it. To summarize, we study the training dynamics of multi-head linear self-attention trained on this in-context linear regression task. We find saddle-to-saddle dynamics, and we identify the in-context learning algorithm in different stages of learning, and they are actually principal component regression in context with increasing number of principal components. So it's like consistent with the common intuition or folklore that like transformers develop increasingly sophisticated in-context learning algorithms during gradient descent training, except in this case, we know exactly what increasingly sophisticated means. It means principal component regression with increasing number of principal components. So with that, we make a theoretical case for the progressive improvements of in-context learning in the gradient descent training of attention models. And there are more results, and like why we have these principal component regression with time in our paper if you're interested. And thank you for your attention.
Thank you very much, Yedi. That was a really interesting talk. Any questions? Yep.
Thanks, super interesting talk. I'm wondering if you change the loss function to something else, how much of this intuition carries over? Like, is there something else it's learning then? Other than the Euclidean loss, that is.
It's a very interesting question, because like usually you use cross-entropy loss, or in the scalar case, logistic loss. But in this case, I'm not too sure about what has happened because I'm doing a regression task, and I cannot really use cross-entropy loss to learn a regression task. So if you change loss, you actually have to change the task here as well. And yeah, I would guess that it still have stages, but I'm not too sure of exactly what happens there.
Any other questions over here?
Thank you for the talk. There's recent work linking the in-context learning property of these architectures with gradient descent. They have shown that the attention-based ICL actually performs one step of gradient descent. So given that you analyzed the training dynamic, did you find something similar in this case?
I think it's consistent with that view. Except that I think in this case, so you definitely can. So we write the solution of this tension model at different stages, and you are able to like define a linear regression model and define appropriate step size and let this be let the solution be like one step of gradient descent of that. One thing that I always find it's a little tricky with the gradient descent view is that that statement only makes sense when you define the model, parameterized model, define the step size and the weights of the model. What do you do gradient descent on, right? So once you define that, basically many in-context learning algorithms can be formulated as doing gradient descent on some loss function with some model parameterized in a certain way. And in this case, we have like explicitly written down like what the attention model does, and I believe that if you choose a loss function and parameterized model appropriately, you can think of that as gradient descent in context.
Great. No more time for questions. Thank you very much, Yedi. Round of applause. So our last speaker is Lisa Alazraki, who is going to be talking about reverse engineering human preferences with reinforcement learning. Thank you.
I'm a PhD student at the Department of Computing of Imperial, supervised by Marek Ray, and this work was done in collaboration with Cohere. So there's quite a lot of literature now showing that the LLM as a judge framework can be attacked in a way that boosts, artificially inflates its scores. And LLM as a judge is extremely popular. It's used to assess different tasks in both verifiable and non-verifiable domains, and it's even used to assess the goodness of new models when they come out. What exists in the literature, though, always appends a sequence of text, appends, prepends, adds a sequence of text to the response of the candidate LLM that has to be scored. Whether that is handcrafted or whether it's tuned, it's always appended to the text itself, to the response itself. And as you can imagine, that means that as effective as it may be in tricking LLM as a judge is also, it can be identified by either human inspection or other automated systems. So what we did instead was to craft an attack to LLM as a judge by using a completely different framework. So we used the judge scores as rewards to tune in a reinforcement learning fashion a preamble generator. And by preamble here I mean system prompt, basically. And these preambles that were tuned are injected into frozen candidate LLMs. And if it's a frozen candidate LLM's generation responses that get scored, that get the reward. So the LLM as a judge reward scorer does not directly observe the preambles. So we call this type of pipeline where we optimize this system prompts through LLM feedback indirectly, reinforcement learning for reverse engineering. So we tuned our preamble generation model as a policy to produce these preambles, given a fixed instruction, which you can see here. So something along the lines of give general advice to help answer this question, a question taken from the training data set. And the goal is to maximize the expected reward of the frozen LLM outputs, which is conditioned on the preambles. And we use the ultra feedback dataset for training. Note that the ultra feedback dataset does have rewards, but we do online learning, so we don't use those. We use discrete rewards on the 1 to 10 scores, on the 1 to 10 scale, elicited by empty bench prompts. And we use contrastive policy gradient as the RL algorithm. So for each given a question, we always sample 2 preambles, and the contrastive policy gradient loss compares. These are passed on to the frozen LLM, makes 2 generations, and the rewards to that are used. The difference between the rewards is used to compute the loss. And of course, as is standard in RL training of LLMs, there's also a KL divergence term, so which penalizes the divergence from the reference policy, which is the untrained model, the LLM. And note that we tune the hyperparameter beta based on the validation performance. And this ends up being quite low. We'll see later the interesting things that this causes. But this makes sense since these preambles are only observed by the frozen large language model, the candidate model. They don't need to be read by humans. So even if they diverge from the reference policy, even if they become unfluent, as long as they produce high rewards, as long as they produce fluent responses from the candidate models and therefore high reward, that's fine. We test this with 3 different pipelines with different preamble generator model and candidate model from both the command and the llama family. And we always use command R+ as a judge, which is a 104 billion model at training. These are the test results. So at test times, we evaluate on MT-Bench, which is a very popular benchmark for the assessment of large language models. Includes several task domains. And we compare our attack with the non-attacked model, but also with attacks that exist in the literature. So you see here verbosity, bandwagon, authority refinement. These are known attacks that exploit known biases of LLM as a judge. And there's also the universal adversarial attack, which instead tunes a sequence of text to be appended to the response. These are on the 1 to 10 scale. So we not only do we obtain like substantial score improvement over the non-attacked model, but we also surpass old baselines. And we also, you might remember, we pass the question from the data set when we generate each preamble. So each preamble is conditioned on the question as well. So as an ablation, we also try to just condition the generic instruction without giving the question. So you end up with the same preamble basically for the entire data set. And also even conditioning on just the beginning of turn token. So not really giving the model anything to go by, just let the reward work its magic and see what comes out. And actually, I don't have the results here, but you can refer to the paper. In both cases, we end up with preambles that still surpass the baselines in performance. So that's interesting. So one thing that is important is seeing how, we train on ultra feedback, we test on MT-Bench, we use the same type of reward. So we wanted to see how well this generalizes to out-of-domain scenarios. So on the left-hand side here, we tried to basically use the prompts tuned with one pipeline, so therefore with a given candidate LLM, frozen candidate LLM, with another candidate LLM and see if they still works. And they do. So they're always above, they always surpass the base model, the unattacked model, and in most cases, the underlined values here, they're also above all baselines. We also try to use different judges that weren't observed at training. So we tried different GPT models, Claude, and again, our attack is actually more effective. Again, above here, I don't have the results, but you can refer to the paper. We also try Arena Hard. So Arena Hard is quite different from MT-Bench in the sense that, well, first of all, it has a different task distribution, but also the reward is computed in a different way. And it's on a different scale. And again, even on Arena Hard, we observe gains using both the Command R judge and GPT-4, which is the standard judge for Arena Hard. We also look at the detectability. So if you remember at the beginning, I said, no attacks that existed are potentially easy to detect. So we looked at how detectable our attack is compared to existing ones. And on the left-hand side, you have human detection rates. And as you can see, our attack to the far right is almost as undetected as the lack of attack. Whereas the verbosity attack is detected approximately 50% of the times, and all the others are detected almost always. We also tried perplexity sliding window filter, which is the standard way of detecting this type of attacks in the literature. And we find also that the false negative rate is very high for our preamble attacks. It's very high also for other attacks, but for example, refinement and authority are detected a lot more often. And the universal adversarial attack, which is the only other tuned attack, is detected almost all of the time. So this is good. Clearly, this works very well, right? One question that I think is natural is, have the frozen candidate LLM responses actually improved by any, metric, or are they just, is this really an attack? Of course, you could argue it's an attack anyway because we are directly exploiting the judge's reward to tune the preamble generator. But is it also, are the answers actually improving, or are they just, is it really just artificially inflated? And it turns out that it doesn't look like the answers are actually improving. So for the verifiable domains, we actually compute the correctness, and we see that the correctness between the non-attacked and the preamble attacked model is very, very similar. And also we have, for all of the domains, including the non-verifiable domains, we have human evaluation. And again, expert annotators rate both outputs almost identically. So it appears that scores are indeed due to improved structure and presentation rather than substance. And we have some examples of these in the appendix of the paper where we show that there's a lot of better formatting and better structure. One thing that I think is particularly interesting, so if you remember, I mentioned the KL divergence coefficient beta ends up being tuned to be quite relatively low. And this is what happens. So we do all the hyperparameter tuning on this command R7B pipeline due to computational limitations. We just do it on one pipeline, and then we apply the same hyperparameters on all the others. So with this beta tuned on this pipeline, when we apply to the llama pipeline, we end up with this gibberish preamble that you see here on the right. And yet, this preamble works. So, this is very interesting to us because also it means that maybe constraining large language models to inputs to prompts that are human readable might actually be overly restrictive from a performance perspective. And yeah, so in conclusion, here we used reinforcement learning for reverse engineering to craft these attacks. We saw it's very effective, but in reality, we imagine that this technique could be used for other applications as well. So including meaningful positive applications. For example, it could use to mitigate toxicity or bias. You could also, here we're optimizing a preamble, a system prompt, so something that comes before the query. But we could also optimize a sequence of different positions. For example, a post-query instruction. We could optimize sequence at different granularity. They could be query-specific. They could be task-specific. They could be domain-specific. So there is a lot, I think, that can be done with this method. And looking ahead, we think that this method could be could find its place in a wider ecosystem where large language models optimize multiple inputs that come from different sources. So, for example, they could come not just from users, but from tools, from other models that are used as auxiliary models, and this could be used to tune responses that are better suited to like an objective that you choose. That's it. Thank you.
Thank you very much, Lisa. We do have time for one small question. Anyone have a question? Oh, did you have a question? Okay.
I was wondering how robust the preambles are. Like, we change one or two words in the question. Does the random text preamble fall apart as an effective attack? And what about the words preamble?
I mean, we did the ablation where we did not pass the question. So we had an ablation where we just passed a generic instruction, and which is something along the line of give advice to answer a generic question. You don't know what it is. And then we had the ablation where we just passed the beginning of turn token. So we passed nothing. And it still outperforms the baselines, which means it's actually quite robust. Of course, the performance is a bit lower, but it's still higher than existing attacks.
Great. Thank you very much, Lisa. And let's just give a round of applause to everyone that talked today. That was a really interesting set of talks. Thank you. So that closes this session, and I believe it's lunch and now a poster session. Thank you very much.